It's Paul again. Here's a short script designed to illustrate Ross's ingenious proof of L'Hopital's theorem as greatly simplified by me. So we're going to deal with a situation where we have to calculate the limit of f of x divided by g of x in the case where at the point where we're evaluating the limit, we have a problem because g of x is 0, but maybe not so much of a problem because f of x is also 0 there. I'm going to evaluate the limit at 1. In the numerator, I have the square root of x minus 1, which clearly goes to 0 as x approaches 1. And in the denominator, I'm calculating the sign of x minus 1. So when x equals 1, I'm calculating the sign of 0. We have a 0 in the denominator also. Let's graph these functions. Here is the denominator function. There is a horizontal line at 0. Here is a vertical line at the point x where we want to evaluate the limit. And you can see that as we approach x from above, g of x goes to 0. Let's plot the function f of x in red. It has the same properties. You know, if you just look at these, you say, looks to me as though the black curve is always twice as big as the red curve. So I would expect that this ratio is always pretty close to 1/2, and it's going to be that in the limit. And that's absolutely right. And if you say, and all I have to do is use the tangent line approximation at x equals 1 to approximate both those functions, you have reinvented L'Hopital's rule. But let's be a little bit more formal about it. Let's invent a new function h, this is the clever part of the proof, which is f of x times g evaluated at 2 minus f of 2 evaluated at 2 times g of x. The choice of 2 is arbitrary. I can use smaller values of x later on in place of 2. But this gives us a function that we can graph and look at. I'm going to multiply this by 10 so that it's easy to see the behavior of the function h. There it is. And it just screams Rolle's theorem at you, doesn't it? Because at 1, h is equal to 0 for the simple reason that both f of x and g of x are equal to 0 when x equals 1. And when x equals 2, we've got f of 2 times g of 2 minus f of 2 times g of 2, which is clearly 0. The function's continuous on the closed interval from 1 to 2, differentiable on the open interval from 1 to 2, has the same value at x equals 1 and 2. It meets all the requirements of Rolle's theorem, and it comes as no surprise, therefore, that there's a place in between 1 and 2 where the derivative is 0, namely the place where the function has its minimum. So we will find that point z by using the optimize function in R. And now I'm going to calculate the ratio of the derivatives. I differentiate f, I differentiate g. I had to do both those by hand because R doesn't do computer algebra. But having calculated the ratio of the derivatives, I can do a comparison. On the one hand, I look at f of 2 over g of 2. And then on the other hand, I look at the ratio of the derivatives evaluated not at 2, but at the point z where Rolle's theorem finds the minimum, the place where the derivative is 0. And you can see the two things are equal. That's the secret of the proof. Substitute any value you like for 2 and do the same construction. You will find a point z that's closer to 1 where the ratio of the derivatives is equal to the ratio of the functions at your original point. And if you take the limit of the ratio of the functions, That's the same thing as the limit as the ratio of the derivatives, and that's why L'Hopital's rule works. For example, instead of 2, I can use 1.5. I define another HE function. I'm going to call this one HH, so that I'm using a different name. The only difference is now I'm evaluating at 1.5 rather than at 2. I graph that. Came as a bit of a surprise to me to discover that this one actually has a maximum, not a minimum, in the interval. But all that Rolle's theorem says is somewhere the derivative is going to be 0, and the optimized function tells us where that is. It's at 1.17. And sure enough, if I take the ratio of f to g at 1.5, that's the same number as the ratio of the derivatives r evaluated at z. We can look a bit more generally at what's going on. Here is a graph of the ratio of the derivatives. I've just plotted that in blue. Here, for comparison, is the ratio f over g, plotted in magenta. It's a slightly different function, but the key point is both those functions have exactly the same limit as x approaches 1, and that's what L'Hopital's rule is all about.